Hi there! I have in the works a video about digital to analog converters. However, that video involves a heavy use of the Thevenin Theorem. And so I wondered, would anybody going to watch such a video if they don't know or have not clear the Thevenin Theorem? And that's how the idea for this video came about. And so, here it is. The Thevenin theorem is a powerful tool for circuit analysis that tends to extremely simplify all the calculations. In general, we can say that if we have a complex circuit made of all linear components connected to a load, RL for example, and we only want to know the current and the voltage across the load, we don't need to solve the whole circuit. Instead, we need to calculate only a couple of parameters that will identify the complex circuit seen as a black box. In particular, we can represent the whole complex circuit with a single voltage generator in series with a single resistance, which we can identify as if it was the internal resistance of the generator. Once we do that, we can just attach to this equivalent circuit the load that we are interested in and resolve this simple circuit, with just one generator and two resistors. The interesting thing is that once we have calculated the equivalent generator and the equivalent resistor, we can easily determine voltage and current through any linear load we apply to the equivalent circuit, without the need to recalculate anything else. Let's continue with the example shown to see how we can calculate the equivalent voltage of this Thevenin generator and the equivalent resistance of this Thevenin resistor. To calculate the equivalent Thevenin resistance, we need to first isolate the complex circuit without the load. Then, we create a new circuit from the complex one, where the resistors are placed in the same position, but any voltage generator present in the circuit is replaced with a short circuit, a simple wire with no resistance. This is because we can assume that the internal resistance of a voltage generator is 0 ohms. In this case, in this particular circuit, we don't have any current generator in the original circuit, so we don't need to do anything about that. But if the complex circuit had also current generators in it, we would have also replaced all of them, but since current generators are defined as having an infinite internal resistance, we would have replaced them with an open circuit, or basically we would have just removed them from the complex circuit. At this point, we just need to calculate the equivalent resistance of the remaining circuit from the perspective of the two leads of the black box. To do that, note that resistors R1 and R2 are now in parallel, which can be better seen if we redraw the circuit this way. And then we have the resistor R3, which is in series with the parallel resistors. The equivalent resistance of this parallel, let's call it Rp, is equal to the product of the two resistances divided by their sum. The full resistance of a circuit R equivalent is now given by the series of Rp and R3, or basically their sum. And so, the Thevenin resistance R equivalent is given for this circuit by R1 times R2 over R1 plus R2 plus R3. At this point, we still need to calculate the Thevenin generator E equivalent. And for that, we need to redraw the circuit without the load and calculate the voltage on the leads of the black box. The voltage over here is the Thevenin voltage. How do we do that? Well, note that since the circuit is open, there is no current flowing through R3, and so the voltage across R2 is the same as E equivalent. But the voltage across R2 is given by E reduced by the ratio of the voltage divider made by R1 and R2, and so we can write that E equivalent equals E over R1 plus R2 times R2. At this point we can finally calculate the current and the voltage across the load by resolving the equivalent circuit, which has become really easy to do. In fact, here is the value for the current, and here is the value for the voltage. You see how now, if we wanted to repeat the calculations for a new value of the load, we would not have to go again through the resolution of the circuit, but we would just need to change the value of the load RL in the last schematic, and therefore change the value of RL in these formulas. And now, let's go to the lab, and let's run some measurements to verify the Thevenin theorem. So, for the lab test, I have these two circuits. This one is the actual circuit with a voltage generator of 5 volts, resistors, 1K, 1K, 1.5K, and a load of 1K. And this is its implementation on a breadboard. And here we have the equivalent Thevenin circuit, where this is the equivalent voltage, the equivalent resistor. The equivalent voltage, doing all the calculations, is basically 2.5 volts, and the equivalent resistor instead is 2 kilo ohm. And this is easily seen because for the voltage, if we remove the load, there is no current flowing through here, so this is just a voltage divider. The two resistors are the same, and so this point here is half the value of this. This is 5 volts, so this is 2.5. The equivalent resistor means this is shorted, and so these two resistors are in parallel. 1K each becomes 0.5K. In series 1.5K makes 2K, and there it is. And the load is the same, 1K and 1K. So let's take a measurement on this circuit and then on this circuit and see if the voltage on the load is the same in both cases. And of course, since the voltage is the same, since the resistors are the same, then the current will be also the same. So let's start setting the voltage for the first circuit. And this is gonna be 5 volts, we said. Okay. Now let's power up the first circuit. This is the positive, it goes this way. And let's check the voltage. This is exactly what we think of over here. And this is exactly 5 volts, 5.0. So let's see now the output of this circuit, which is between here and here. And this is the voltage on the load resistor. Let me see if I can do it easily. So the voltage is 0.8 volts. Now let's change this to 2.5, since that is the equivalent voltage. Okay, so now I'm gonna move power from here to this other circuit over here. Let's check the power supply. This is actually 2.5 volts. And that's the value we have over there. So let me adjust a little bit, so it's going to be exactly 2.5. Okay, that's good enough. Now let's go back here to the equivalent circuit, and let's measure the voltage to the load, which is on this side here, and here. It should also be 0.8 volts if we did everything correctly. And in fact, there it is. It's actually 0.83, but probably we didn't adjust very carefully the voltage on the other side. So let's try again with the 5 volts just to make sure. Let's see if we obtain the same thing. So now we have to change here, go back on the previous circuit, right here, there we go, and now we can measure this voltage here, which we need to increase a little bit, so let me do that. Okay, and now let's measure the voltage on the load one more time. So we can do it actually right here on the load. Probably it's easier to deal with. Oh yeah, it's definitely better. There we go. So they match perfectly. Good, and this confirms that the Thevenin Theorem is effective in doing this kind of calculations to solve the circuits. Today we have learned the Thevenin Theorem, and we have seen its efficient way to resolve circuits when we need to find the voltage and current only on a specific component rather than the whole circuit. The theorem also allows us to quickly replace one component with another and recalculate the voltage and current for the new component without having to resolve again the whole circuit. Now that we have acquired this new knowledge, you will see this theorem used soon in future videos, where you will have the chance to better appreciate how powerful it is to help solving certain problems. And with that, I'll see you in the next video, and in the meantime, happy experiments!